Hello guys, welcome to SOH, the best office hours ever, because you are part of it. This is AP Physics 1, 2024, and problem 5, and there is a collision. So let's see how we solve this. Probably there is a collision with elastic, yes, elastic. There's this graph, which is a graph of time in terms of space, okay, and then there is stuck together, so inelastic. Okay, and then, oh, this is the thing, right? The center of the mass. That's sometimes a bit tricky. So let's begin by reviewing the main concepts that we have in this problem, and then you may leave, solve it, and come back, or you can look at how we solve it for some of these questions too. So let's see. A block A slides along a horizontal surface towards block B. Ooh, it's coming, which is initially at rest. Okay, it's not moving. Good for it. Now, the masses are 6 and 2 kilos. Okay, awesome. Good numbers, right? Probably. The blocks collide elastically. So what happens with an elastic collision? In an elastic collision, you have conservation of kinetic energy. Kinetic energy is conserved. Elastic. Okay. Now, also in an instantaneous collision, you have conservation of linear momentum. Okay, that's always. But if it's elastic, in addition to that, you have conservation of kinetic energy. Remember that kinetic energy is 1/2 of mv squared. Okay. Alrighty, and there is no friction. Okay, cool, fine, easy. So determine the speed of block B after the collision. But look, they say that the kinetic energy is 9 joules after the collision. So thank you so much, right? Because 9 joules is 1/2 of the mass of B, v squared. And since this is 2, so we have this, and then you get, oh, be careful with that, you get 2 signs. In this case, of course, it's going to be plus, moves to the right, but let's make sure that this is understood, because it can be different in other situations. So we have this block, and it collides against this one that is coming here. So assuming that positive is in this direction, then we know that it's going to move towards the right. So this is the right answer, and then towards the right. At least towards the right-hand side. That does not depend on the sign convention. But this is the answer. End of the story, we're good. What happens next? Oh, be careful. We have a graph that has the distance here and time here. So what does it mean for block B? It means that it's all the time, so this means rest. This means at rest. All the time is at 2 meters. It's not moving. What is this thing then? Well, this is telling us how much does block A move in 1 second over in which what distance, right? So we have like in 1 second 2 meters, so it would be like 2 meters per second. Okay, so this is the kind of graph that we are looking at. Let's read it. On the graph in figure 2, draw and label 3 lines, so be careful with that, 3 lines, to represent the positions of block A, block B, and the center of mass. Well, we have here the center of mass, that they already did it for us. Maybe we can check at the end if you want to see whether it's correct. As a function of t between 1 and 2 seconds, and label them with different labels. Okay, so let's see. Let's begin with block B. Why with block B? Because we know that the speed is 3 meters per second. So we know that after 1 second, so look at that, this is 1 second here, it's going to go up by 3 meters. So 3 meters here, plus 3. So it's going to end up here, right? So this is going to be block B, okay, block B, or let's say, B, block B. Now, the next thing I'm going to deal with is the center of the mass. Why? Because the center of the mass does not change. The speed, the center of the mass, the velocity of the center of the mass does not change in an instantaneous collision. We can talk more about it if the collision is not instantaneous, but let's first solve it. So if it doesn't change, basically, what will happen here? In 1 second, it goes up by 1 meter, right? So in 1 second, goes up by 1 meter. So, or by 2 meters, sorry. So you have this, right? Well, let's do it right. Let's do it right. Basically, it doesn't change. So what you have to do is simply follow this line. That's it. Indeed, in 1 second, it moves like 1.5 meters probably. But we don't know. And you don't need to know. You just need to, same line. You just need to say that. We will compute it. It was kind of mentally computing And yes, we can derive it. And then finally, what happens with A? Well, it would be nice to know, well, we need to know what's the speed of A after the collision. So how do we do that? Well, this is a graph of X versus T. So somehow we can get the speed of A. That's the tricky part. That's the tricky part. So from here, initially, it may look very simple, but it's tricky. So imagine that you are in the test and you don't know what to do. You look back. Do they give me the speed of A before the collision? Because of course I need to find after the collision, and you don't find it. This graph is telling you. So remember that. Why? Because we have that block A did 2 meters in 1 second. So 2 meters in 1 second. So that's the initial speed. How do we find the final speed? Because that's what we need to do the plot, right? So you know that it's elastic. So remember that we were using here, you know that if it's elastic, there is conservation of kinetic energy. So since it's elastic, you have that K initial equals K final. So at the beginning we had 1/2 of the mass, 6 of A. This is speed. That's a tricky part, right? Because we need the other one was addressed, and then we know that it's 9 joules for, and then you have here 1, 6, and the speed that we want to know at the end. This is the final one, right? So what do we have here? 12 equals to 9 plus 3 VA squared, and that's very nice because VA squared equals to 1. Now this is tricky because VA could be plus minus 1 meters per second. So how do you know which one is correct? Well, I mean, honestly, this plot, if it would be negative, then how it will go like in this direction, right? So down. As time moves forward, it will cover less distance. So yeah, it could be positive or negative. We need to think about it. So let's see. In instantaneous collisions, this is the ones that you're going to consider always, except, you know, in college, sometimes if you have like a collision with an incline, the incline may move, or a collision on air, and it lasts for some time, so gravity can do an effect. You know, very difficult problems that you may find out or not, depending on where you go. So instantaneous collisions, and we can solve that if you want. Just write in the comments. Yeah, please solve one that we don't have an instantaneous collision. How to deal with it? So instantaneous collisions, there is conservation of linear momentum. So we have this. And let's compute how much was at the beginning and how much is at the end. So at the beginning, what do we have? We have this, all this is at the beginning, right? And this is at the beginning, initial. And then all this should be equal to this, oops, at the end. Yeah, almost there. And then, what happens at the beginning? 6 kilos. You found the speed at the beginning, it was 2 meters per second. This guy was addressed, and we also found that this guy that is 2 kilos was moving with 3 meters per second, right? And then you have this mass. So what would you plug here in order for this to work? The sign plus, right? So then we have discovered that VA is plus 1 meter per second. So to the right, to the right hand side. And this will help us finish this plot because in 1 second it moves 1 meter. So the next second, it will move 1 meter. So this is A. Okay? And we are done. This is a beautiful plot that you can do, and it's amazing. Now, what happens next? Well, we could check, but that will be for the end. We could check whether the center of the mass is like that, and so let's leave that for the end. The next question says, consider if in the original scenario, instead of colliding elastically, they both are stuck together. What does it mean, stuck together? What does this mean? You know, stuck together. It means that it's totally inelastic. Totally inelastic. What happens in that case? K is not conserved. So forget about using that equation. But P is conserved. Okay? I mean, again, it's an instantaneous collision. So, what is the question? Describe how the line drawn on the center. Okay, so if this conserved, the center of the mass is conserved, it doesn't change. The speed of the center of the mass does not change. I mean, indeed, the velocity, or the vector. You can take this for granted. It's something that, in principle, you have studied in class and so on. So it basically doesn't change. So it would be the same. Okay, the same as before. So yeah. that's it. So in principle, that's it. Now, can we measure this center of the mass with the information we have? Yes, we can. Can we verify that this line is correct? Well, let's see. Let's see if we can do that. How can we derive the speed of the center of the mass? It doesn't change, but let's compute it the initial, before the collision, and then after. So that by definition, we have this, right? That's the definition of the speed of the center of the mass. And then you have that this was 6 kilos, and before the collision, we found out that before the collision was 2 meters per second, right? 2 meters per second, positive, and this guy was at rest. And the sum of the two masses is, 8, right? But 6 plus 2, 8. Just make sure that everything is fine. So what we have is 3/2 of meter per second. So in 2 seconds, it does 3 meters. So indeed, in two seconds, 3, but they started here too. So okay, it would be 3.5. That's where we ended up, more or less. We'll see why these two, this point here. But to begin with, 3.5, looks reasonable, because this could be half, 1.5 in 1 second. Yes. So 1.5 meters per second. That looks reasonable. What happens at the end, final one? Well, we have to do the same operation, but with the final numbers. This was 1 meter per second, positive. We found it, positive. Let's be positive. And then plus 2 meters multiplied by 3, again positive. There's always positive. And then multiplied by 8. And you get the same, 12 divided by 8, which is, again, 3/2. So yes, it is conserved. So that's amazing. Now, why does it start here in the middle? Well, let's compute the position of the center of the mass. The position of the center of the mass is a similar expression, but instead of speeds, you have positions. Okay? Well, that's not so clear unless we have the positions, right? We can always choose one of them 0, like our reference, but did they show how apart they are? Not, but we are super smart, right? Because, okay, let's choose this like 0. Or, I don't know, yeah, that doesn't matter, this is like 0. Where is the block B? How long does it take to collide? 1 second. That's the time that you take to get the solution, right? In 1 second, we have this block that was moving initially with which speed? We found it out, right? We found that it's 2 meters per second. So indeed it's 2 meters away, because it's 2 meters per second takes 1 second, it's 2 meters away. Let's see if we catch these guys. So what do we have here? Let's go. Let's see if we catch them. So mass, 6, position, 0, just because we say that that's where is A is 0, like they did here. Plus 2 kilos, multiplied by, let me delete this happy face here. Sorry about that, we will be happy later. Well, let's just add it here, happy, and we're always happy. And then XV, 2 meters, divided by 8. Oh man, they did think. Okay, well, worth the $100 some that we have to pay. Good for them. Okay, we're good. We're the best. Hey, see you later.